Hello, good people. Welcome to video one of topic 6.8. 6.8 is I'm following Brian Passwater's suggestion of breaking it into two parts. The first part here, we're going to look at basic anti-differentiation rules. And so I want you to think about what we did most of the first semester was take derivatives, right? We found all these, a list of rules to use whenever we were looking for the instantaneous rate of change, also known as the derivative. We just use those rules. And so now we're going to reverse the process. And we're going to call these antiderivatives. So I'm going to say antiderivatives, or some people call them indefinite integrals. Indefinite integrals. And you're going to see in a little bit why we call them indefinite integrals. But antiderivatives and indefinite integrals are the same thing. And if we remember that derivatives and antiderivatives are reverse operations, kind of like addition and subtraction, right? We add a number to get an answer. We subtract that number from the answer, and we get back to where we started. We multiply by a number to get an answer. We take that answer and we divide by the number, and we get back to where we started. So derivatives and antiderivatives work in the same vein. So just a quick recap of taking the derivative. We learned rules to find derivatives such as this. So I can figure out what f prime of x equals. What is the derivative of x squared? Using the power rule, we can get the derivative is 2x. What would be the derivative f prime of sine x? Using the trig rules, we found the derivative of sine x would be cosine x. And then what would be the derivative of 3? Well, that's a constant, and the derivative of constant is just 0 because the function itself, 3, never changes, so the rate of change would be 0. So that's the basic rules that we learned in the first semester. But now let's think in reverse. So let's say g prime is equal to 2x. What would be a good equation for g of x? If g prime, the derivative of g is 2x, then what would be a good equation for g of x? And if you look at number 1, that can kind of help you gather a possible answer, because one possible answer could be that g of x is x squared. But I say that because it's not the only function whose derivative is 2x. I'll let you think about that. Could you think of another g of x, another function, that when we take the derivative, it equals 2x? Now, you might be thinking of a whole different type of function, but what if it's a quadratic with a constant added on? These functions are not the same, right? And yet, when I take the derivative of this, because I take the derivative of x squared, I get 2x. I take the derivative of 6, and that's 0. Well, then I get this derivative, this g prime. Or, what if I subtract? Minus 10. And so the reality is that if I can add or subtract any constant to the main function, x squared, I can produce another function whose derivative is the same. So all of these have the same derivative, and the derivative is that. So instead of writing all possible answers, what we do is we write what we call a general solution and say the original function gx could be x squared plus some constant. That constant could be a positive number, it could be a negative number that then transforms it into like a subtraction situation. And so here we call this the general solution. And later when we deal specifically with differential equations, we'll find that this general solution will help us solve problems if we know an initial condition. But that's in the future. So the moral of the story is Working backwards and finding the antiderivative means that for any function that I can find the antiderivative, um, the main antiderivative for, I can always add a constant and it would also be an antiderivative. So we just write the plus c for all cases. So knowing that, given h prime, can we find h of x? It says you may have to use trial and error on a few of these. Okay, well, let's try this. Can you go back in time, or can you go backwards and find what was the function whose derivative of that function is cosine of x? So the derivative of blank is cosine of x. What is that blank? If you said sine of x, you're correct. But it could also be sine of x plus pi. It could be sine of x minus 3. It could be sine of x plus 5,237. So we're just going to say h of x could be sine of x plus a constant. So for all of these antiderivatives that we find, we're always going to need to add that plus c to signify that it is not just one possible solution, but an infinite number of possible solutions that could be the original function. Okay, what about this one? Can you think of a function whose derivative is negative 2? Can you go backwards and can you find that? If you said negative 2x, you'd be correct. But remember, we have to put the plus c. So for all of these antiderivatives, we're going to do a plus c add-on to get that. I'm going to come over here to letter D. Letter D is find the derivative of, well, if the derivative of h is 0, find the original function. So what would the original function have to be so that its derivative is equal to 0? The derivative of what is equal to 0? And for this one, we know that it's just any constant. The derivative of any constant is equal to 0. And then over here, the original function whose derivative is negative sine x, well, that would be cosine x plus c. And so I'm going to have you see if you can do c and f over here. Can you guess and check what those might be? And in the next video, we'll check them, and then we'll kind of see if there's a more general process to doing things like antiderivatives for c and f.